Hey there, and welcome. If you're getting ready for an exam or you just want to really understand naval electronics, you are in exactly the right place. Today, we're going to build a solid foundation on naval radar systems, breaking down the essential concepts you absolutely have to know. So, let's get started and decode the electronic senses of a modern warship. When you look at a warship's mast, it can just seem like this confusing jumble of shapes and antennas. But here's a better way to think about it. Every single one of those antennas is a highly specialized sense organ for the ship. Together, they let the ship see and understand its environment for hundreds of miles. In this explainer, we're going to figure out what each of these senses does and what it's telling the crew. So, what is radar, really? I mean, at its most basic level? Well, the name says it all: radio detection and ranging. Here's how it works. The radar sends out a quick pulse of radio energy. That pulse travels out, hits something, like another ship or an airplane, and a tiny bit of that energy bounces back. The system measures the time it took for that echo to return, and boom, it knows the object's range, how far away it is. And since it knows which direction the antenna was pointing, it also knows the bearing. This simple idea is the absolute bedrock of everything a modern warship does, from navigating safely to defending itself. It's the ship's eyes. All right, here's our game plan for this study session. We'll kick things off with surface search radars. Then we'll look up to the skies with 2D air search. After that, we'll step it up with 3D radar, see how it all looks from the operator's view, and then we'll wrap it all up with a quick recap and review to make sure it all sticks. Okay, first things first. Let's focus on the most basic fundamental job a radar has: seeing what's on the water immediately around the ship. This is the world of surface search and navigation radars. A surface search radar, well, the name kind of gives it away, doesn't it? It's designed to search across the surface of the ocean. It's a two-dimensional or 2D system. That means it gives us those two key pieces of information we just talked about: range, which is distance, and bearing, which is direction. You can think of it like it's creating a flat top-down map of everything around the ship. A perfect example of this is the ANS SPS-67. Now, you might think its main job is just spotting other ships so you don't collide, and yeah, it does that, but its primary mission is way more critical. This is a key defensive tool. It's designed to spot fast, low-flying threats. We're talking anti-ship missiles. Its ability to find those targets quickly and automatically is absolutely vital for a ship's survival. Okay, I know a block diagram like this can look a little intimidating, but it actually shows a really elegant process. You can just trace the path of the signal. See, it starts in the transmitter, goes up to the antenna to get sent out, the returning echo gets caught by that same antenna, and then it's sent through all the processors until it finally pops up as a little blip on an operator's screen. It's just this constant, super fast loop of information. So that all makes sense for what's on the surface. But what if the threat isn't a boat on the water? What if it's a jet, way up in the air, hundreds of miles away? For that, you're going to need a whole different kind of sense. And to answer that question, we need to look up. So let's jump into our next section: scanning the skies with 2D air search radars. Now, just like the surface radar, a 2D air search radar gives you range and bearing, but its mission is totally different. This thing is designed for incredible long-range performance, to reach out hundreds of miles and spot aircraft. But here is the crucial point, and this is a big one for any exam: what it doesn't provide. It cannot tell you the target's altitude. It knows something is out there, but it has no idea how high up it is. The classic example here is the ANS SPS-49. This is basically the Navy's long-range eye in the sky. Its entire purpose in life is to give early warning, to see potential threats when they are very, very far away. It's also built like a tank, designed to punch through bad weather and electronic jamming. And critically, it acts as an essential backup if the ship's more advanced 3D systems ever go down. And a diagram like this really gives you a sense of the physical scale. I mean, look at that massive antenna on the right. That's what gives it that incredible range. And then you have all these different cabinets and consoles that are needed to power the whole thing and process those incredibly faint signals that come back from hundreds of miles away. It's a whole lot of hardware just to do one thing: give an early warning. So we can see on the surface, and we can see way out into the air. But we're still missing a key piece of the puzzle, aren't we? It's time to add that third dimension. This slide really lays it out perfectly. On the left, you've got your 2D radar. It tells you two things: how far and which direction. But the 3D radar on the right adds the absolute game changer: elevation. It doesn't just see a target, it knows exactly how high that target is. So why does this one extra piece of information matter so much? Well, think about it. You can't guide a missile to hit a target if you don't know its altitude. You can't safely direct your own friendly fighter jets if you don't know how high they are. Elevation is that missing link that turns radar from just a detection tool into a sophisticated system for controlling weapons and air traffic. All right, so now we have all of our data. We've got range, bearing, and elevation. In our next section, let's look at how all that data gets put to use, from some highly specialized tasks to the basic displays an operator looks at all day. Landing a jet on an aircraft carrier at night in bad weather, it's one of the most demanding jobs in the entire world. That's where carrier-controlled approach, or CCA, radars come in. Systems like the AN/CSPN-46 are incredibly precise. Their entire purpose is to guide a pilot safely onto a tiny, moving runway, in the dark, in the middle of the ocean, even when the pilot can't see a thing out the window. So how does an operator actually see all this information? On the left, we have the PPI, or Plan Position Indicator. This is that classic 360-degree top-down radar map you always see in the movies. It shows you range and bearing. But on the right, you've got the RHI, or Range Height Indicator. This is how you visualize that all-important third dimension, altitude. It gives you a side-on view showing how high a target is. A full 3D radar system gives you the data for both of these views. The bottom line is this. These scopes, these indicators, they are the bridge between all the complex electronics and the human brain. They take those raw, invisible radio waves and turn them into a picture that an operator can understand and act on, whether that's just navigating the ship or defending it from an incoming threat. We have definitely covered a lot of ground. So now, to help all this sink in for your studies, let's run through a real quick recap, and then we'll test your knowledge.
All right, let's do this rapid fire. Ready? Radar, radio detection and ranging. Surface search, 2D, for targets on the water. 2D air search finds aircraft using just range and bearing. 3D radar adds that elevation data. CCA for carrier landings. PPI scope, that's your top-down view. And RHI scope, that's the side view for height. Got it? Awesome. Okay, time for a little quiz. Feel free to pause and think about the answers. Question 1. What are the two primary functions of a surface search radar? Question 2. What is the main difference between a 2D and a 3D radar? And number 3, which type of radar scope gives you that 360-degree top-down view? And here are the last two questions. Number 4, what information does an RHI scope provide that a PPI scope does not? And finally, number 5, what is the primary purpose of a carrier-controlled approach system? If you can answer all those, you have a really solid handle on this material. We'll leave you with this final thought to chew on. We've talked about how a ship sees with its individual senses, surface search, air search, 3D radar, but the real magic happens next. How does the ship's combat system take all that separate data from all those different senses and fuse it all together into one single coherent picture of the world? That's the next level, and maybe a topic for another time. Thanks for joining me.